So continuing from our last video, in this video or in this chapter, we will cover the different antenna types and also a couple of concepts of visual line of sight and RF line of sight. Quick recap of what antennas really are from the last video. An antenna is a device when connected to a transmitter, it converts the AC signal to RF waves. And when connected to a receiver, it converts RF waves into AC signal. That's what we did in the last video as well, right? If you remember, this is the job of an antenna. Now, there are different antenna types which are used in the Wi-Fi world. One of which is very common, which we've all heard about, is an omni antenna, an omnidirectional antenna. Okay, so think of it like this. It radiates the RF signal equally in all directions, like a light bulb. If a light bulb is connected to a ceiling, it will send out RF signals in all direction, right? Or it sends out light in all direction. This is the omni behavior of this antenna. Okay. The other one is, or the second one is a semi-directional antenna. This antenna is like a torch, or it radiates the energy in a specific direction. Let's say a torch is like this, and the signal is sent out in a specific direction like this. A semi-directional antenna is usually responsible for connecting two buildings or connecting the wired networks of two buildings. Uh, you know, Something like this at a distance of up to, let's say, up to 2 miles, not more than that, up to 2 miles. Okay. Uh, when you talk about omni antenna, you must have heard about rubber ducky antenna, which is the default antenna on pretty much every AP which is using omni antennas. A rubber ducky antenna. Something wrong with the pen, but anyway, yeah, rubber ducky antenna. Now, when you talk about semi-directional antennas, there are multiple examples of that as well. A semi-directional antenna like a patch antenna or a Yagi antenna. These are common examples of semi-directional antenna, and they can go up to a distance of 2 miles approximately. The next one is called a highly directional antenna. Okay. Now this one is responsible for connecting, making sure communications happen up to a larger distance, which can go all the way up to approximately 34 miles or approximately 58 kilometers. Okay. Now that is why we use highly directional antennas. So think of it like a laser beam. Okay. You are focusing the energy in a specific direction. You must have played with laser beams when you were a kid. So it is used to focus the energy in a particular direction at a longer distance or till a longer distance. That is the example of a highly directional antenna. Examples of which are sector antennas or parabolic antennas, right? So for cable TVs connecting to the satellites, they use parabolic antennas, which are highly directional antennas, right? Okay. So these three types of antennas are responsible or are used widely in the Wi-Fi world, which are put on the APs for different use cases. Now, what I want you to also understand in this is an example of an omni antenna. Let's say the Omni antenna comes with a standard gain. We want to make sure that we increase the gain, for example, of the Omni antenna. Okay, it can look something like this. So this is the antenna. Okay, this is the coverage pattern of an antenna, of an Omni antenna when looked from the top. Okay, now if let's say this is the antenna with 2.14 dBi of gain. So the gain is represented by dBi. Let's say the antenna is with a gain of 2.14 dBi. If we increase the gain of this antenna, what we are doing is we are increasing the horizontal range of the antenna. Okay, like this. We are making sure that horizontally the coverage increases, but vertically, right from the ceiling to the ground, the coverage the coverage decreases. Okay, so let's say this is a 5 dBi gain antenna. So what we are doing is we are actually pressing it from the top and increasing the coverage horizontally, whereas decreasing the coverage vertically. If we go one step further, let's say we have an antenna with a gain of 9 dBi. Okay, 9 dBi antenna gain. It becomes even flatter. So it is going even further away horizontally, so we can cover a larger distance in the corridor, but vertically the range further decreases. Okay, so you need to keep this in mind when you design a Wi-Fi network. If you're placing an access point on the ceiling with a 5 dBi gain or a 9 dBi gain, you have to understand that the coverage may expand or is good enough for a corridor, but it may not be able to reach these subsequent floors. Like if you're placing an access point on floor number two, then that coverage may not reach floor number one or floor number three. Okay. So you need to keep these things in mind when you design a Wi-Fi network based on the kind of the how much gain you add on the antenna. So that's the behavior of the Omni antenna, and how you can play around with the gain to, I mean, depends on what use case it is. If you're putting an AP on each floor, then yes, you can play around with high gain. But if you have a common AP for two floors, depends on the customer requirement, then you've got to make sure you play with the gain properly, right? So this is a little bit about the different kinds of antennas that we have. One important thing, and then in fact a couple of concepts that come to my mind now are depending on the visual line of sight and the RF line of sight. These are two different things. We'll talk about visual line of sight first. Okay, now when we have communications happening, and this is usually this makes more sense in outdoor communication. Of course, in indoor communication also you need to make sure that the visual line of sight from a transmitter to a receiver is quite clear. Okay, there should not be anything in between. So a transmitter should be able to see a receiver properly. There should be enough and clear visual line of sight, from the naked eye. That's all it is when it comes about, when we talk about visual line of sight. There has to be a clear line of path from the transmitter to the receiver. That needs to be clear. There should not be any obstruction in between. That's the visual line of sight. But for a communication between a transmitter and a receiver, visual line of sight is not enough. We also have something called an RF line of sight. Okay, not a lot of people focus on this, but it is extremely important. RF line of sight is also known as the Fresnel zone. Okay. Now, it simply means I'll explain this with the help of an example. Let's say this is a transmitter and this is a receiver. Now, the RF line of sight is like an American football that is created from the transmitter to a receiver, okay? And there should not be any obstruction in this RF line of sight. This is like a Fresnel zone that we have created. Now, there are two Fresnel zones. One is which is closer, the first one. The other is slightly wider. This is called the second Fresnel zone. Fresnel zone number one and Fresnel zone number two. So they are both like American footballs, but it is said that, or it is advisable that when you create a communication between two buildings, the first Fresnel zone should not be the first Fresnel zone should not be 20% or more occupied. Anything beyond 20% will make the link unreliable or will cause effects, will be harmful for the communication. Anything around 40% is going to make the link unreliable, not going to work. So if you connect two antennas on two buildings to communicate to each other, and let's say in some time we have some, we have another building that came up in between here, or let's say some trees grow, or any obstruction came in between, we have to redesign. We have to make sure that yes, at each point in time, there is not more than 20% of the 20% Fresnel zone is not occupied, or if it's 40%, it's going to be unreliable at all. Okay. So that's what RF line of sight is. It's like a Fresnel zone which we have to take care of. And so these two, I mean, RF line of sight and visual line of sight, they both need to be clear for the link to be reliable and for RF communication to happen properly. Right? That's very critical. Keep this in mind because a lot of people miss out on the Fresnel zone, especially in the outdoor area where, let's say, forests, because we have trees in the forest, so we have to design it very, keeping a lot of things in mind, very carefully. And this usually happens in areas where there are too many high-rise buildings, there is a forest, or some other regions where we are expecting that Fresnel zone may not be completely vacant. So keep that in mind, guys. Cool. So we'll continue in the third chapter. Thank you.